So this is a more or less short homemade lecture. I'm just going to give it a try of explaining of like how hot can it get on our planet, because some people are afraid, like with all the threatening news from global warming, that we might suddenly get like 60 degrees Celsius or 70 degrees Celsius on our planet, or 80 degrees Celsius. We'll keep this in Celsius, so those people who use Fahrenheit need to have like just get something to calculate or have a chart next to them. So will it get up like to 60 degrees Celsius, 70 degrees Celsius, or 80 degrees Celsius? Will we just like die from heat on our planet when global warming proceeds? Well, it can bring some peace. It's not going to happen that easily. And the reason is because we have to just to find like the answer to our question, we have to go to the tropics. And if we go to the tropics, like the equatorial tropics, around the equator, this is where the sun is the highest, where the elevation of the sun is always the highest on the planet, where the most energy is gained. So the equator is always the hottest place on the planet, where most energy is gained, where most heat is produced, and where also the warmest air of the planet must be generated. So all around the equator, this is the place where the warmest air of the planet is generated. And this also defines what the warmest air of the planet is. So it's a very large area that's affected by this, because this is all around the equator, is already a large area, and this warm air tends to spread north to the poles, north and south to the poles. It covers a large area, especially in higher levels. It covers a large area of the tropics and the subtropics. This is the tropical air, the warmest air of the planet. And this air is kind of usually has this level that we see here, -5 degrees Celsius at 6,000 meters of elevation. That's the temperature we usually find in the tropical air. And this is the warmest you get on the planet. You don't really exceed this. This is just really like a plane of a similar temperature with very little change locally. It always remains on this level because it spreads uniformly like a blanket. So if we have climate change, if climate change should affect this level, it needs to affect it all over the planet. This cannot happen locally. This cannot happen for one summer. This needs to happen permanently and entirely over the whole planet. And only then this temperature can go up. Practically, if we get the whole planet to get 2 degrees warmer, these are the values that the science is usually talking, not about local areas, but the whole planet getting 2 degrees warmer. Yes, then also this gets actually up 2 degrees. It's in reality a bit more, but it's a different story. So not much more than this. We maybe get like, instead of -5 degrees, planet warms up 2 degrees, we maybe get -2 here, or -1 or something like that. So that's a bit warmer. It's not drastically warmer. And so the question we have now in front of us is like, most of us know that in the tropics, in the rainforest and tropical oceans, it's like maybe 30, 35 degrees. It's not as hot as in some of the desert areas where temperatures, most of us will have heard about that, temperatures go up to 40 or even 50 degrees Celsius. So how is that possible that places do get hotter, even though we, like I said, we have this one uniform warmest air over the whole planet? How is it possible that it actually gets warmer than these tropical 30 degrees? A simple, or more or less simple answer to this is because of humidity. It's practically, the thing is that a lot of heat is stored in humidity, in water vapor. That's why we also feel that when air is very humid, we also feel like, oh, it feels, even though the temperature is not so hot, it feels hotter. We can even feel it as humans, that a lot of heat is stored in water vapor. And another good example to feel that is when we take a shower or we swim in a lake and we go outside and our body's wet and we walk around and don't immediately dry our bodies. We'll feel that we feel cold, and sometimes we enjoy that effect to cool down. So this is because evaporation of water needs energy. And so when the water evaporates from our body, it removes some of our air energy and we feel colder. And so when the same water that evaporated suddenly condensates again, like in form of clouds or in form of fog or in forms of drops, like on a cold car surface or so in the night. All these kinds of condensation processes, same heat is released again. So practically when the air rises up and forms a cloud, and the moment the cloud starts forming, the temperature doesn't cool off so fast as it usually would with altitude. So this is quite kind of a very fundamental thing to metrology. We have the so-called dry adiabatic and wet adiabatic lapse rate. That's what I'm talking about here now. You don't need to remember these words, but usually if we go up with height and there's no water engaged, it's just totally dry, we get this rate, like 1 degree per 100 meters. That's how it usually cools off with altitude. So practically that means we have here at sea level, let's say 30 degrees, you go up 1,000 meters on a 1,000 meter high mountain, you have 20 degrees. If the mountain is 2,000 meter, you have 10 degrees. If the mountain is 3,000 meter, you have 0 degrees. And this rate of cooling with altitude is changed if a cloud forms, because then all this condensation heat is released. So we have here, as an example, we have here 1 kilometer, 20 degrees Celsius. We have the cloud base actually here at 1,000 meters. And then the air continues to rise in the fog, and all this condensation heat is released, and we get 16 degrees at 2 kilometers. We should have had 10 degrees here. We have 16. So we have 6 degrees more. And that's a major difference. It's a lot of energy released. And that explains why in the equator it's not that hot in temperature, because we have lots of humidity. We have these tropical thunderclouds, and we result maybe the clouds being 1,000 meters above the ground, very low down, rain showers falling, and we get a surface temperature of 30 degrees. It's because we start from this uniform general level in the tropics, and then we go down in the cloud, in the fog, and let's say the cloud goes all the way down to sea level. Let's think about the extreme condition that practically it's so wet, like in the middle of a storm with rain falling, that the cloud practically touches the sea. Then we have a temperature of around 24 degrees in the tropics, 25. It's like always the same. Maybe it's a degree more or a degree less, but not a big change. And it also, here's another value, which is here the same, because we're in the cloud. This is the so-called dew point value. This means when you have, for example, you have a beer, and the beer is very cold, and in this case, the beer doesn't even need to be very cold. The beer needs to be less than this low. If the beer has 23 degrees Celsius, then already on the glass that you already have these water drops forming. So your beer will look like it's nice and cool and refreshing, but actually it might be as warm as 23 degrees Celsius. You will still already have drops. So it's because it's a very high level of humidity. Usually we don't get this. Usually we get maybe, clouds. The air is not totally saturated with humidity, so it rises up, and it rises up maybe 1,000 meters before clouds start forming. So the clouds are still low, but not so very low. And then from 1,000 meters, where we have this 20 degrees here, typical tropical value, we go down and we have 30 degrees at 1,000 meters. So if we go a little bit further inland, where it's even drier, and we're further away from the rainforest and from the ocean, some savanna area, so we might get the clouds forming at 2,000 meters, 16 degrees, 2,000 meters down, 1 degree per 100 meter, we get 36 degrees at sea level. And with 3,000 meters when the cloud level is at 3,000 meters, we get 41 degrees. And cloud level is 4,000 meters, 46 degrees Celsius. So this means the cloud will only form at 4,000 meters. So you will see a cloud forming on the top of a very high mountain range and no lower. So this is already very much like a desert climate, where there's just not enough humidity. And then you get this temperature resulting from the dry adiabatic lapse rate from 4,000 meters down to sea level, resulting with 46 degrees Celsius. So this is already very much desert heat. In reality, it even gets a little bit warmer because you always get like a warm pillar on the surface, so you can maybe get 49 even under these conditions. But that's kind of like a relation. You know that if you want to get it hotter, because the tropical area remains always the same, if you want to have hotter temperatures, the surface needs to be drier, the air needs to be drier. So the drier it gets, the hotter it gets. Invalid for these like tropical areas. If you have strong enough sun, anyhow, so the sun power is not a limitation, then the only limitation is the level, and you have tropical air in higher levels, which is mostly the case in the tropics and the subtropics. You get in the summer especially, then you get practically the level of humidity as defining how hot it can get. So the hotter, the more dry. The more desert, the more hot. It's practically really connected to the level of humidity. So this also can tell you something about these questions of how hot it can get, because these conditions relating to hot, like a desert where it's dry inside, like the topographic conditions creating a desert, are not going to change. And I'm going to come to this now to explain it a little bit further. So if we want to have these hot conditions, we need the following conditions. We need, or circumstances, we need enough strong sun that has the power to heat it up. The sun needs to be high enough, cannot be really like far up north, or cannot be in winter. And we need to have very dry conditions, that there's no lower cloud forming. And we also need to make sure that we far enough away or cut off from a colder area, because what we get here is this situation we have when we have, for example, a hot area that is theoretically dry, and sun is strong enough and could heat up inland, and we have an ocean pretty close, and there's nothing in the way. It's like a flat area, and maybe this ocean has 30 degrees Celsius, and here we already have, because it's drier, we get 40 degrees Celsius. Then here it's wetter, and it's also the water temperature itself preventing it from heating up, because water always stores heat, so it warms up much slower. It's another factor engaged. But what we get here is that slightly colder air is more dense. We get practically higher pressure here, and hot air is less dense. It's like that's why a hot air balloon goes up, because hot air is less dense. So here we have hot air is less dense. We get a low pressure area. This is called a heat low. We always have that, like in interior Spain, interior Sahara, interior India, everywhere it's interior and gets very hot, it's a heat low formed in summer. And so it can also be in small islands. Even then, interior has a small, tiny little heat low, and that will cause a so-called compensation flow. That means from the colder surface, like the ocean, the wind will start moving inland and drive that heat away. So you need to be sufficiently far away from the ocean to prevent this from happening. Otherwise, you also do not get these hot temperatures. You can either be very far away, or you can be still quite close but cut off through a major mountain range. This is a very typical situation. Imagine this is like a circle of pretty high mountains, or like two chains connected to each other, and between them there's a low-lying area. So this area, because this comes at ground level, this compensation flow, it cannot get over these high mountains. It stays underneath and it's hotter above, so it's cut off from getting in here. And you get the mountains, the mountain tops are like heating up. They're kind of, you can also think about the mountains being practically like the sun doesn't need to start. Let's start from here. The sun, we have minus 5 degrees at the 6,000 meters, and then you have a mountain that's already 3,000 meters high. So the sun doesn't need to heat up all this low level, all this air level underneath. You're already higher up. So it also can heat up easily, and it can heat up higher. And you get already on the top of these mountains, you get high temperatures, and you do not get this cold air to get anywhere in this interior basin. So the interior basin is cut off from the cooler compensation flow, and can heat up very much. And that's usually the kind of situation that you get when you get really hot temperatures. You have a desert area somewhere in the subtropics usually, and it's an area that is surrounded by very high mountains, and inside this very high mountain range you get a basin that's lower down, cut off, and it's already by nature a desert because these high mountains surrounding it from both sides will prevent the clouds from getting inside, because the mountains are a barrier, so the rain doesn't really get inside this area so easily, and all the humidity. So this will by nature usually be already a very dry area, and so it will be just perfect for predestined for like getting very hot temperatures. Death Valley is an example in California, or the Turpan Depression in China, or the Sahara, which is very far inland, and it's also cut off from the Atlas Mountains, at least to the northwest. So these areas get temperatures up to 50 degrees Celsius, because here we get enough sunshine, we're far enough away from the ocean, which brings humidity but also brings the condensation flow, and we also possibly cut off by some mountain ranges, so it can heat up even more. And these topographic conditions obviously do not change with climate change, so these conditions are not going to change. So practically this results in my previous answer that we do not suddenly get 60 degrees or 70 degrees Celsius, these global maximum temperatures, because the conditions of dryness in the interior desert doesn't change through global warming. What practically happens is only this temperature goes up, and this, like I explained before, needs the whole planet entirely to warm up. If this whole planet warms up 2 degrees, this maybe warms up 3 degrees, also related to the humidity, and that's a bit more. So we have maybe -2 degrees here, and then this 3 degrees more will add to the highest temperature also of the planet. So instead of having maybe at the moment peak temperatures on the planet of around 55 degrees Celsius, we might get to 60 degrees Celsius in future with global warming. We have like a rate of extra heat comparable to the general level of the planet heating up, not like suddenly 20 degrees more. We don't get suddenly 70 degrees. We get, instead of 55, maybe up to 60, unless the surface of the planet changes. So this is pretty much a fact. So we don't have to be afraid of the planet temperatures soon going anywhere above 60. Yet we have another story where the rate of heating is actually a bit higher than the general rate of the whole planet warming up. So we see that in many like further northern areas, like in summer, in continental areas like Canada, United States, Europe, maybe Argentina, and these continental Russia areas, we suddenly get hotter summer temperatures, especially in those areas which usually had more like cooler ocean winds. Suddenly we get these exceptional hot periods in the middle of summer, and the temperatures are actually rising. Suddenly is really a lot higher than usual. Like we get areas that used to have peak temperature of 35 suddenly go up to 40. We observe that in some parts of the planet, and suddenly summer heat waves are much more drastic. And why is this? This is like a different issue that's here. Mostly it's related to the jet stream. And the jet stream, probably most of us have heard about it somehow. That's like a river of fast-flowing air that's formed between the tropics and the cold polar areas, North Pole, South Pole. Here also we have these two rivers circling the temperate areas. This river of air, this fast-flowing river, is what creates the changing weathers in the mid-latitude. These like typical depressions with cold fronts and colder air and warmer heat waves and cold waves, and this changeable weather that's in the temperate zone. This is created by this moving jet stream that moves like like a river. This is a warm area, this is a cold area, and they move like rivers, meandering river over the surface. And this river is the energy it receives is from the difference between the warm south and the cold north and south, cold polar areas. The difference creates this stream. It's because this again is warmer air, it's less dense, it's more like the same mass of air goes higher up, and this is colder air, it's more dense, so the same mass of air goes not so high. So you practically get a mountain of air, of air here, and like a valley of air there, and you get practically a pressure gradient that creates this a bit more complex through the Coriolis effect, but it creates this. Is, for the moment, this is sufficient to know. It creates this this meandering stream of very fast winds in the temperate zone, and now the issue we have here, and that's why we get these drastic changes, is because here we have ice and snow. In the polar areas we have ice and snow. And ice and snow is white and reflects. There's some other factors involved, but the major factor is ice and snow is white and reflects a lot of sunlight back into space, so it prevents heating up. It's if you get global warming, then you don't only get the general amount of warming on the planet, but you also get ice to melt. So you practically here in the polar areas, you get less ice and you get more dark surface, you get more heat gain. So these areas here in the polar areas, they heat up stronger than the tropics, where the tropics has this uniform area that needs to heat up all in total. And here the melting ice will contribute to that to a faster rate of heating. And this is quite a lot of a difference. And so practically the contrast between the warm tropics, which heat up just a little bit, and the polar areas, which heat up much faster, gets less. So practically the energy that is available for this meandering stream of air becomes less. So instead of a fast-flowing dynamic river that tends to change also very fast, we get a much more slower stream of air that also tends to stand for a long time over the same area. It's much less dynamic. So it means it also tends to stand a lot longer, like hot air areas. They still change, still changes between cold and warm, but a hot air areas, for example, this is like here, this is like a bump of hot air that moves north. This stands a lot longer over one area, and if this happens by chance to be a continent and it stands for a long time here, the conditions are much more favorable even in further north areas in summer for these practically desert hot conditions to establish. They can just temporarily establish, even in an area where in winter there's still enough rain and humidity. In summer it can heat up so much that it suddenly gets these very exceptional hot summer temperatures. And that's because this stream that brings a lot of changes, and that also brings a lot of mixing, that the ocean air is moved inland and then the land air is moved over the ocean, so it makes a lot of compensation between the continent and the ocean. This compensation is less because the jet stream is weaker, so we get more like constant cold areas, more commonly constant cold areas over the ocean remaining over summer, and constant hot areas over the continent. And we get this continental, practically the continental summers, or continental areas that have cold winters and warm, hot summers. Those continental areas start to spread up closer to the ocean because the energy of these ocean winds moves less inland, has less power. And so the heat waves that used to be much more farther inland suddenly get more close or get more north than they usually used to be. And this is one of them. It's one of the most drastic changes that comes through global warming. So locally, temperature heat peaks can go up faster than the global heat, which is practically only like global extreme will not go up much more than the general rate of global warming on the whole planet. So like I said, from 55 to maybe in the future 60 in the hottest places of the planet. Just kind of giving a number. And though in some temperate areas where it used to maybe reach 30 degrees in the past in summer, suddenly we might locally get areas which the temperature suddenly reaches 40 degrees, so it heats up faster. The heat peaks go up faster, and that's what we can actually observe in some areas like in southern Europe and in the Mediterranean, and also in most continental areas inland of Europe and inland of Canada and so on. We have these like quite exceptional hot temperatures in summer because of the weak jet stream. And it also explains the longer periods of wet and dry weather, so you get more flooding and you get more drought events, because the weather patterns tend to remain more longer time over the same area. Okay, so that's me for the moment. I hope I could create some understanding of this matter. Ciao, this is Tim Vaitari Heidenreich speaking in July 2023. Ciao.